In this video, we present our recent paper towards Markerless surgical tool and hand pose estimation. Our motivation for joint hand tool pose estimation is the fact that tracking hands and surgical instruments becomes increasingly important in clinical research. Knowing the exact pose of surgeons' hands and surgical instruments paves the way for new applications that can optimize the outcome of a surgery by providing surgical guidance, reduce the likelihood of intraoperative complications via automated human error detection, and reduce the radiation exposure for patient and staff. Such use cases depend on the comparison of the current hand and tool poses with the preoperative and patient-specific plan. However, strict regulations for operations in operating rooms, such as certifications required for new hardware or the protection of patient-specific data, complicate the collection for realistic training data which is required for state-of-the-art deep learning methods. In this paper, we focus on visual pose estimation of surgical instruments in the operating room. For this scenario, we assumed an egocentric perspective because a head-mounted camera provides a close and unobstructed view on the instruments and the incision without obstructing the surgeons in any way. Also, this perspective allows us to later deploy the tracking system on a mixed reality device such as the HoloLens. We decided to only use a single RGB camera, as monocular RGB cameras are still the most common optical system in today's operating rooms and can be deployed at low cost. As the instruments are always held and occluded by the surgeon's hand, joint hand-tool pose estimation might be beneficial for the model's accuracy due to the explicit attention on the hand pose, which incentivizes the model to also learn grasp characteristics such as relative poses of hand and instrument. In our paper, we propose two data generation pipelines. First, we implemented a synthetic data generation pipeline to create realistic RGB patches for our scenario. Second, we propose a semi-automatic labeling pipeline to create a real dataset, which can be recorded in a mock-up operating room. We focus on drilling as an exemplary application, as bone drilling is conducted in about 95% of orthopedic interventions. Using these pipelines, we generate a synthetic and real dataset for the Colibri 2 medical drill, which you can see in the video. Both datasets can be used for joint hand and tool pose estimation. We follow previous literature and use synthetically generated data to compensate the lack of existing datasets. This first requires to define a set of synthetic grasps. Surgical instruments are designed for only a limited number of plausible grasps, for example, indicated by ergonomically formed handles. Therefore, it's feasible to predefine these grasp templates and only augment them with little noise later on. We use the parameterized Mano hand model within the GraspIt simulator to verify the physical and biomechanical plausibility of each generated grasp. We combine the tool model with the SMPL-H model in a Blender scene. While the hand parameters are set to a randomly selected grasp that was generated in the previous step, the remaining body parameters are sampled from the surreal dataset. We enrich the rendering with real background images taken from existing operation videos. Last, we render RGB images of the scene from an egocentric perspective by placing the virtual camera at the SMPL's head location. To capture realistic data for a real dataset, we use a setup consisting of two calibrated and hardware-synchronized Azure Kinect cameras in a mock-up operating room. We execute typical drilling trajectories and capture them from an egocentric perspective as well as from a lateral point of view to minimize occlusions. We lift the RGBD frames of both cameras to 3D and align the resulting point clouds to obtain a dense 3D representation of the operating table and the workspace. For every recorded drill trajectory, we manually label one initial frame by registering the tool model with the point cloud via ICP. Then we crop the hand from the point cloud and merge its points with the 3D model to obtain a combined representation of hand and tool. As the applied grasp is embedded in this combined model, we hereby assume a rigid connection between hand and tool. This assumption is valid as long as the tool is held firmly. To recover the ground truth pose for all subsequent frames, we align the combined hand-tool model with the point clouds via ICP, using the previous frame's pose as initialization. Using the recovered ground truth tool poses, we extract RGB patches which are approximately centered at the tool's bounding box center. Using both presented pipelines, we generated a synthetic and a real dataset. Here you can see a side-by-side comparison of a few randomly selected samples. For the synthetic dataset, we manually defined 7 grasps and rendered 10,500 frames. For the real dataset, we recorded 11 drilling sequences. For increased diversity, we used 2 pairs of differently colored rubber gloves and let 2 different users operate the drill. The real dataset consists of about 2,300 frames. All samples have a resolution of 256 by 256 pixels. We trained and evaluated 3 baseline models on our datasets. First, we used PVNet, an object-only pose estimation model, which recovers the 6D pose indirectly by estimating a dense vector field of 2D unit vectors that point towards predefined 3D key points on the object's surface. Our second baseline is the joint hand-object pose estimation model by Hassan and others, here called hand-object-net. It uses a shared ResNet encoder and 2 decoder branches to directly regress hand and object pose parameters. To evaluate whether PVNet's keypoint-based pose estimation is beneficial in our scenario, we additionally evaluate a combination of the first 2 baselines. Hereby, we replace the object decoder branch in hand-object-net with PVNet's decoder branch. As both models use a pre-trained ResNet 18 as their encoder, the network architecture of the combined model only differs from the PVNet architecture in the presence of the hand decoder branch. We evaluated all baseline models on our synthetic and real dataset. We observed that the domain gap between the 2 datasets is still significant, and it was therefore necessary to refine all models on real data after pre-training them on the synthetic dataset. After refinement, the best model achieves an average 3D vertex error of 13.78 mm. PVNet's keypoint-based pose estimation approach yields significantly worse results than the direct regression of rotation and translation parameters used by hand-object-net. We observed that hand-object-net also learned to predict consistent poses for hand and tool, which always resemble plausible grasps. In contrast, the combined model failed to do so because the different representations of hand and tool pose used in the combined model impede any comparison and its extraction of relative pose features. To conclude, we contributed 2 pipelines that can be used to create synthetic and real datasets for joint hand-tool pose estimation. We evaluated exemplary datasets on 3 baseline models. The best performing model achieves an average 3D vertex error of 13.78 mm. The models do not yet meet the stringent accuracy and robustness requirements of clinical applications. However, they rely on only a single RGB image and can be extended in various ways to improve their performance. As future work, we want to extend the pipelines, datasets, and models to more modalities such as depth and video. Thank you for watching. If you're interested, you can find our code and datasets at medicalaugmentedreality.org.